So this is the solution manual for assignment 5, starting with question 1 here. A ball is launched vertically upwards at 20 meters per second upwards. Part A. At what time does the ball have a vertical displacement of 15 meters upwards? So, starting off, we are told that we have an initial velocity of 20 meters per second upwards. We know that acceleration due to gravity is 9.8 meters per second downwards. And from our kinematics equations, we can use delta D equals initial velocity times delta t plus 1/2 a delta t squared. We are asked at what time does the ball reach a height of delta D equals 15 meters upwards. So we have initial velocity, we have acceleration due to gravity, that is g in our case, and we have delta D, so we can plug these numbers in and solve for time. So here we get 15 equals 20t plus 1/2 times 9.8 t squared. I'm dropping the delta here just for simplicity. I'm going to move that 15 over. I'm going to get 0 equals negative 15 plus 20t plus, sorry, I should have a negative here. Acceleration due to gravity works in the opposite direction as the initial velocity here. Its acceleration due to gravity is downwards, so I need to have a negative, so that will become negative 4.9 t squared. Here we have a quadratic. We are looking to solve it now. So we're going to have t equals negative 20 plus or minus 20 squared minus 4 times negative 4.9 times negative 15 all over 2 times negative 4.9. And solving this gives us two solutions. I'll do one in green, one in blue. One of them is t equals 0.99 seconds, and the other gives us t equals 3.1 seconds. So here we end up actually getting two solutions. And for part B here, why does it make sense that there is more than one correct answer? This is because it reaches 15 meters upwards on the way up and again on its way back down. So the ball reaches 15 meters as it goes up. It ends up going higher than 15 meters, and it ends up passing 15 meters again on its way back down. Each of these times, the first time is at about 1 second, the second time is at about 3 seconds. So that's part 1A and B. Now 1C, sketching some graphs. So let's get to it. I'm going to do my 3 graphs like this. First one is displacement in meters versus time in seconds. Then I have velocity in meters per second versus time in seconds. And lastly, I have acceleration in meters per second squared versus time in seconds. So let's start with displacement. I know that this is essentially projectile motion. Even though you're throwing it straight up, it's still a projectile. It still undergoes projectile motion. And we can model this with a parabola where our displacement starts at 0 and it reaches 15 meters at 2 points here and here. We know the time of these 2 points is about 1 second and about 3 seconds. And that's all I wanted from one graph. Now let's do the same for the others. Velocity. It's going to have an initial velocity of 20 when it first leaves a person's hand. So it's going to start up here at the top. We know that at the peak, it has to be at 0, because at the peak it's at rest. And then when it comes back down to where it was originally thrown from, it will have an equal magnitude and velocity, but opposite direction. So it will look like this. And my horizontal axis at 0 is in the center there. Labeling my graph again. Here I have 1 second and 3 seconds. So, going to acceleration now. Our acceleration is constant at negative 9.8 meters per second squared. So we just have a constant horizontal line at that value. And where it reaches 15 meters again is, of course, going to be at the same times again. And that was everything for part 1. For question 1, parts A, B, and C. Question 3. Calculate the total distance from this graph here. Now, something I did not notice until I went to go start marking is that I forgot to give you guys a numerical value for where this line intersects 0 here. Now, to me, it looks like about 1/3 or 1/4 of the way. For simplicity's sake, I'm going to call it 4, because that's what I was originally thinking when I made this question. Now, whatever you ended up choosing, I just gave it to you. Whatever you eyeballed, I just gave that to you. Assumed that it was correct, because I didn't give you the number. My bad. I'm going to use 4, though. So, if, and I'm going to zoom in closely here, if you take a good look at our velocity time graph here, you will see we have area A, B, area C is this small little triangle right here, and then area D is our rectangle. So we got 3 triangles and 1 rectangle. We need to calculate each area. The reason I need area for distance, so distance is area on a velocity versus time graph. So that's how I know I need my area. I know that distance, you get distance by calculating the area under the curve. Now, it's not always under the line. It's actually the distance, the area between the line of your graph and the 0, the axis. So for A and B, you're going to find the area underneath. But for C and D, you're actually going to find the area above, this area here. So let's get calculating. I know I'm going to have 3 different areas. I'm going to have A, B, C, and D. For A, this is a triangle, so I know I'm going to be using the triangle formula of 1/2 base times height. My base goes from 0 to 3, so my base is 3, and my height goes from 0 to 10, so that's 10. For B, again, triangle, so 1/2 base times height. My base goes from 3 to 4, so that's 1, and my height goes from 10 to 0, so 10. And just because the line is going down does not mean it's negative. That area is still above the 0. It's still above the 0 axis. It's still in the positive range of velocities. So it has to be a positive area because it's above. C is where it's going to start being negative. So again, it's a triangle, so 1/2 base times height. The base is from 4 to 5. So again, that's 1. But our height goes from 0 to -5 here. So my height is -5. And that's where our negative area is going to be coming from here. D, just a rectangle, base times height. Normally, no 1/2. This goes from 5 to 10. So I know I'm going to have 5. And the height is 0 to -5. So I get, -5 here. Equaling all of these out, I get 15, 5, -2.5, and -25 as my numbers here. And we are looking for distance. This is a scalar. So for distance, this is total distance traveled. So we need to look at the absolute values of these numbers. So it's going to be the absolute value of A plus the absolute value of B plus the absolute value of C plus, you guessed it, the absolute value of D. So all of these, it's going to be 15 plus 5 plus 2.5 plus 25. And that's going to give us a total distance of 47.5 meters. Done. Part B, how does your answer change if asked to calculate the displacement instead of distance? So now this is a vector. The answer changes by now we do not take absolute values and keep the signs for direction. And if you're curious, the displacement ends up being -7.5 meters. You may go ahead and try that on your own. So here, part C, calculate the acceleration for each of the 3 line segments. I'm going to call this A in blue, B in blue, and C in blue for each of the line segments, just using a different color here to break it up. So our acceleration is going to be the slope of each line. So acceleration from a V versus T graph is slope. So for part A, for part B, and part C, I'm going to go ahead and calculate them separately like this. So for A, we're just going to use rise over run. We'll use this method here. Rise over run, not rum. Rise over run. And if we go back to the graph, we see that it rises from 0 to 10, and it runs from 0 to 3. So we have a rise of 10, a run of 3, 10 over 3. And we know that acceleration for part A is equal to 3.3 repeated forever meters per second squared. Boom. And I'm just going to divide these so it's nice and clear. For B, we will use the point slope formula here. So m equals y2 minus y1 over x2 minus x1. And looking up here, our first point is going to be the very top of the graph, the maximum, the absolute maximum, which is going to have an x-coordinate of 3 and a y-coordinate of 10, both positive. And then our endpoint is going to be right at the bottom here, where it reaches the lowest point for the first time. And that's going to have an x-coordinate of positive 5 and a y-coordinate of negative 5. So plugging in those numbers here, we get negative 5 minus 10 over 5 minus 3, which gives us negative 15 over 2, which is the same as negative 7.5 meters per second squared. And that is the acceleration for part B. For part C, the acceleration is equal to 0. This section of the graph has 0 slope. It is horizontal. No calculation needed. If you really wanted, you could pick 2 points where you have an x value of 5, and for your first point, x value of positive 5, y value of negative 5. For your second point, x value positive 10, y value negative 5. And then when you plug it into our point slope formula, you get negative 5 minus negative 5 on top and 10 minus 5 on the bottom. This ends up being 0 divided by 5 equals 0. So, if you don't believe me, there's the math to prove it. So this was question number 3. Also, apparently I skipped number 2. There is no question number 2. Oops. Oh well. Okay, so describe what could be happening in this graph. So I see 5 distinct sections here. I'm going to call it sections A, B, C, D, and E. And I'll write just a quick little statement for each one. So for section A car accelerates increasingly and we know this because this is a velocity time graph, and this first section is actually curved. It's exponential, which is going to give us a linearly increasing acceleration for this section. And it lasts for 10 seconds. B. The car drives at constant velocity for 10 seconds. Excuse me. Part C. Car decelerates to a stop over 5 seconds. D, car is stopped at rest. A bit redundant there, but whatever. for 5 seconds. And then lastly, car accelerates backwards for 10 seconds. So, great. There we go. Short little, I would say sentences, but honestly, these aren't even really completely grammatically correct or fully completed sentences. But luckily, that's not what I'm marking for. So this was an example solution for number 4 here. You could have done any example, could have chosen anything. I think most people chose car because of my little example statement up there at the top. And that's totally fine. If you use something else, that's totally fine as well. Overall, I think this question was very well done. Question 5. The Daytona 500 is a race where cars are driven for 200 laps around a 2.5 mile track. What is the total displacement of a race car when they cross the finish line? A little bit of a hint here. The question is worth 1 point. Usually means it's going to be a quick, short, easy answer. In this case, that's exactly what this is. Total displacement, the start and finish are at the same location. So total displacement is 0. 6A, use Google, any mapping app, or AI to find how many kilometers apart Niagara College and Bobcaygeon, Ontario are. Is this a distance or a displacement? I used Google Maps, and it gave me a distance. It was about 300 kilometers. Displacement does not make sense because displacement would mean drawing a line straight from the college to Bobcaygeon, which would cross Lake Ontario. So displacement, or let's say traveling the displacement. Traveling along the displacement would mean flying over land, forest, a lake, and other obstacles. The big reason why this doesn't make sense is this is not how you would actually get there. Because there is no airport in Bobcaygeon, so it doesn't matter where you fly in from. Of course, I guess you could also just hike through woods and across roadways and take a boat directly across the lake and any rivers that you come across and just travel in a direct straight line to get there. But that's just very infeasible. It would take you much, much longer. So the distance is given by any sort of map or mapping app, so long as you don't specifically tell it to give you a displacement. It should give you a distance by default. Some of you actually got ones that gave you a displacement, and absolutely great, gave you the mark for that too. It either way is correct here. I used Google Maps, it gave me a distance. As long as whatever you said was correct for your scenario, I gave you the mark. So you could have said displacement and still been correct for part A, but a displacement does not make sense to use no matter what your mapping app or AI or whatever told you. Also, kudos to those of you who actually admitted to using AI, even though I told you you're welcome to use it. So thanks. Anyway, number 7. Why is the following not an example of constant velocity? This is because in circular motion, I should say uniform circular motion in uniform circular motion, speed is constant, but the direction is constantly, that is the worst H ever, changing. Therefore, it is accelerating. And velocity cannot be constant. And that was it for assignment 7. Overall, I think, or sorry, not assignment 7. That was question 7. This is assignment 5. That was it for assignment 5. Overall, I think this was mostly done quite well. And thank you for taking the time to listen. If you did, I'd appreciate it if someone could let me know if they actually listen through all of these and how the quality is. If you hear different noises in the background, hopefully I can mitigate those. But from what I can tell, I think they're fine so far. Anyway, thank you for listening, and check out the next assignment soon.